So, short question today. It's about force. What is it? Define force. Who can help me out without being too complicated? Just a few words you need to define force. What is it? Star Wars. Alexa, what are you saying? And what is that motion? Push or a pull, exactly. Force is a push or a pull. It's too bad the folks at home don't hear my dad jokes.
They don't?
No, I turn it on afterwards. You're missing quite a show.
Say it again. We'll do a fake laugh. We'll do a fake laugh. All right.
Okay. It better be a good fake laugh, though, okay? So, I decided to go on a diet the other day. And it's a brand new diet, just starting to try it out. I only eat aircraft. So far, it's been a little plain.
That was a good one.
Did anybody hear this morning about the dead cartoonist?
No.
No?
Yeah, I killed him.
So apparently Max killed him, and so far the details are a bit sketchy.
Oh, that was a good one.
Maybe we should do this. I should be recording this.
It means you have to get a laugh out of it, right?
Yes, you do have to laugh from now on.
Yeah.
You should have them post the jokes in like a submission.
No, they should send a video of them laughing.
Yeah.
Like a little ha-ha and send it.
Sure. That might be an idea. Yeah. Okay. So, despite, Max, now that we know, is a murderer, what I'd like you to do is find a group of 2 or 3 people and grab yourself a whiteboard, please. And if you team with Max, beware.
Still see her in church every day. Or every Sunday. She knew Billy, you have no power here.
There's gonna be like a group of
Group of 4 is fine.
Mr. J. did.
Do it fast, like.
Dickman was by far my least favorite.
So, I know what you guys have been missing since last year, and that is force diagrams. We are going to be looking at force diagrams once again in this chapter, though the good news is that they're really not getting much more complicated. It's pretty much the same story. All those weird angles that we did, those are all going to be pretty much the same. It's not going to be any more complicated. But we do have to make sure that we're on the same page when we start the whole story over again here. So I figured we should break up the force diagrams because by the end of that chapter, everybody seems pretty sick of them. So we've got a little chapter that we're going to be doing right now called force. The last one was inertia with those force diagrams, and that's what we'll be beginning today, our force chapter. So I've got a little fan cart here. I can turn it on, I can turn it off, and it moves if I do that. So what I'd like you to do first is on your whiteboard, I want you to draw 3 force diagrams. One for when the fan cart is off and at rest, 1 for after it's turned on and starts moving, and then 1 for when it's turned off again and continues to move. So like there. So for the folks at home, it's like when it's at rest, when the fan cart is turned on and is moving, and then the last force diagram is for after it's turned off, it continues to move for a while. So those 3 force diagrams, let's see what you can do. Go. For this example, we'll say that you could ignore friction. I'll be using them in an example.
Take it.
30 seconds, finish up those drawings.
Where it's turned off.
Yep. All right, everybody, hold up your whiteboards, please. Let's see what you did. Looks like most groups have the same correct answers. So, let's go through these step by step here. So when the object is off and at rest, all we have is force of gravity and normal force. Those are the 2 forces when it's off and at rest. Once it is turned on and is moving to the right, we continue to have those 2 forces. In addition to that, there's a force to the right. Will that be a tension force or an applied force? Yeah, it's going to be an applied force because that air is pushing on the object. So it's moving to the right. Yes?
Why are there 3 ends?
Oh, whoops. Gravity down, normal force up, applied force to the right. Now, once it's turned off, we've got gravity, we've got normal force, and if you assumed that there was no friction, that's all you would have. If you're assuming that there is friction in these cases, you would have some friction to the left here and some friction to the left there. Questions on these first force diagrams? Okay, erase your whiteboards. Got another scenario. New scenario. So the fan cart begins off, and it's moving to the right. Then the fan is turned on, and it slows down. So it's moving to the right, then the fan's turned on, and it slows down. So those two things I'd like you to draw the force diagrams for. For those of you at home, fan cart is moving to the right, the fan is off, and the fan is turned on, and that makes the cart slow down.
Are we assuming there's no friction again?
Yeah, let's assume there's no friction.
Okay, yes, because he's not going to throw it across the table. It's still coming that way, but it's getting pushed back that way. It's still going in that direction. And it'll start getting pushed back.
So when it be on this side? Are you pushing it or is it just moving it by itself?
It's starting in motion. I'm not touching it the whole time. Alrighty, let's see those whiteboards. Hold them up nice and high. Alright, very good. Okay, I see some different answers for this one. So let's take a look at this step by step. So, when the fan cart is off and it is moving to the right on its own accord, we've got gravity going down. We've got normal force going up. And because I'm not touching it, I'm not actively pushing or pulling on it, we have no other horizontal forces. The main thing I want to emphasize here is just to remind you guys again that just because an object is in motion does not mean that there must be a force acting on it. Because an object in motion will naturally stay in motion until something else acts on it, like turning on the fan. Once you turn on the fan, we've got gravity, we've got normal force, and if it was originally moving to the right and the fan is causing it to slow down, it is providing an applied force in the direction opposite the motion. So this is what you should have for these. If we were considering friction friction would be a little bit to the left here, and you'd have an extra force to the left here. But like we said before, we can ignore friction for this scenario. Okay, you can get rid of those. Let's do one more.
I was sweating my cheeks off in overtime. Second I hit that final shot, I was just like, yep, GG's. I'm in the back of the goal being frantic for no reason. Goalie, I came back and saved it like 4 times. You were like, that's your chip, and then I'd save it, and then you'd be like, that's your chip, and then you'd be all the way on the other side. The other side of the field, like almost inside the goal.
All right. Next scenario. This will be the last one you're doing force diagrams for today. The fan begins on. The first part of the motion is while I am pushing it. The second part of the motion is I let it go and it slows down. The third part of the motion is it comes to rest. So again, it's on and being pushed for number 1. I let it go and it slows down 2. And then when it comes to rest, that would be the third force diagram. See what you can do with those. For the folks at home, the fan begins on. I'm actively pushing it for the first force diagram. When I let it go, it's going to slow down and then eventually come to a stop. So those 3 spots I would like force diagrams for. No, I mean I only got one hand, so I'm only pushing it. Oh, I see what you're saying. You can have 2 applied forces, yeah. The fan and the hand. Alrighty, let's see those whiteboards. Hold them up for me, please. Alright. Okay. Very good. Thank you. Okay. Most groups have the right idea on this, so let's take a look at it together. So, eyes up here, folks, keep it down, please. So when the fan is on and pushed, we've got several forces acting. Gravity's there like always. Normal force is there like almost always. Now I'm pushing it to the right, so there's an applied force in this direction. In addition, we've got the fan itself that's opposing that motion. So you also would have an applied force to the left. Now, because my push is causing it to speed up, that force would be larger than the opposing force from the fan. So you could just label these as both applied forces. You could put a little subscript, whatever. But they are both pushing forces, so they are both applied. That's what force diagram 1 would be. While it slows down, much of these forces remain. Gravity, normal force, and as it slows down, the applied force from the fan remains on it. And this is one of those scenarios that can be tricky because the fan cart is moving to the right, and even though it's moving to the right, the only horizontal force acting is one to the left. So that is possible. It does sound like a little bit of a paradox, but it is true. When it comes to rest, do we have a force that's horizontal when it comes to rest? Yes, we do, because the fan is still on.
Friction.
But friction could be there too. But we're going to ignore friction for now. As far as the fan goes, though, as long as the fan is on, it's providing that force. So what I really want you to make sure that you're taking note of here is motion does not always indicate what forces are present. Here, we're moving to the right, but we have no forces to the right, just one to the left. Here, we're at rest, so you might think we don't have any horizontal forces, but we do. We have that force from the fan still active. So make sure that you realize that, and I've got one more activity that hopefully will really drive this home. Erase all of your force diagrams, please. All right. So, I promise you, this is the only graph you will see in this chapter.
Okay.
You're welcome.
Like
Thank
this
you.
specific graph on the
This specific graph.
This type of.
This is the only graph I'm going to ask you to do in this chapter. I'm sure you guys are graphed out by now. So, overall, excellent job on the test. The average scores were really good. It seemed like I actually had more perfect scores on this test than I've had on any test this whole school year. That being said, there were several people that really did struggle. So you do need to make sure that you're seeing me if you have difficulty with this stuff. But one thing that's kind of interesting to take note of from those graphs in the last chapter, what you're actually doing when you were doing those graphs, how many of you in here are not in calculus? Raise your hand. Those graphs are basically graphical calculus. You're doing integrals and you're doing derivatives when you're going between those three graphs. That's something we'll learn more about if you're taking AP Physics next year. But, so if you had trouble, that's okay. Graphical derivatives don't come easy for everybody. But yeah, be proud of yourself. So this graph, I would like you to show me how the overall horizontal force changes on this object when it goes through 3 phases of motion. The fan is on the entire time now. It begins by moving after I let it go. It slows, it stops, and it speeds up in the opposite direction. And I want you to show me how the overall horizontal force changes over that period of time. So again, time starts the instant it leaves my hand. And now time stops. So it starts after it leaves my hand. It is slowing down because the fan's going against it. Then it stops, turns around, and speeds up in the opposite direction. So how does the overall horizontal force on it change as time goes on? Does it go up? Does it go down? Does it go to 0? See what you can do. So you can kind of think of your graph like this if you want. It's slowing down for this entire first part here. Then it's at rest, and then it speeds up in the opposite direction.
I saw Bongo in time for the first person. I was like, dang. I saw him, I was like, oh my god.
She did like this. I'm going like this.
All right, everybody hold up your whiteboards, please. Thank you. Okay. So, let's think about what's happening on the forces for this example. The reason that I go over this is because, listen up please, the reason I go over this is because it is a big area where there are a lot of misconceptions on force. Looking around at the whiteboard diagrams that you guys have, it looks like most groups are overthinking this. And that's why I bring it up. Because when we're looking at what's happening with this particular scenario, what's the horizontal force here? It's the fan, right? Is the fan changing at all the whole time? No. So if in your gut, when you first started this, you thought maybe it's the same the whole time, you are absolutely right. Now the point I need to drive home here, and the point I have to make sure that that's very clear before the end of the day today, is that motion does not always represent force. You've got an object slowing down. It is coming to rest. It is speeding up. And through that entire path, there is only one force that's acting horizontally. It's the fan, and the fan doesn't change. So even though the motion changes, we have to make sure that we recognize that the applied force does not change. So simply because we have a change in motion does not mean we're going to necessarily have a change in force. Go ahead, wipe off your whiteboards, put them away, and head back to your seats.
Okay, right. No, if you have first of all,
You better receive that chip.
this is
Okay, chew that.
this is the car. This is Anna. This is the curve. Here you go, Anna. Boom. Pass it down. Pass it down. So, pass it. Keep your leg across. Instead of going like this. And pull it right.
That was the only graph.
So you like okay, girl.
That's
That might actually be the last graph you do all year. I don't know. Definitely this chapter.
What's our final?
Well, the final's the questions again.
Oh,
Ooh, yeah.
yeah.
Okay. So just to kind of wrap this up and put a nice little bow on it, I want to kind of bring it back to the beginning of when people started describing motion, and that was with mostly Aristotle. You know, he believed that objects moved because they had their own natural place: earth, air, fire, and what was the other one? Earth, air, fire, and wind. Yeah. So they each had their natural place, and they would go to their natural place without any other force acting. Later on, they found that that didn't accurately describe motion in a lot of different ways. So then the Galilean model came in. And the Galilean model, which kind of started at the beginning of the Middle Ages, is one of those models that's easy to get confused about because it seems like it would explain things very well. Basically, what it said is that when an object is moving, there is a force in the direction of the motion. And as the object slows down, that force decreases. So it sounds like it makes sense, but when we actually apply it to real scenarios, it doesn't match up with what works. What does match up with what works is the Newtonian model, which is where we are now. And in the comparison would be Galileo would say that when you roll a bowling ball, eventually it's going to come to rest, and as time goes on, the force that you imparted to it will remain with it and decrease as time goes on, as it slows down. Newton would just say that once it leaves your hand, there is no imparted force to it. That object is given a certain velocity, and it decreases over time due to friction. And if there was no friction, it would not decrease over time. That's what Newton's first law is all about. So I just want to make sure to drive that home one more time before we get going again with these force diagrams. Simply because an object is moving does not necessarily mean you have a force in the direction of the motion, even though it's pretty tempting to say that. So, okay. Last thing I'm going to do today is hand out our project for this chapter. You're welcome. So, I'm going to give you some advice on this project challenge. Anybody watching at home, here it is. You can find it in the Force folder, in the Laws of Motion folder. So Laws of Motion and then Force. So you can read the description yourselves. The main thing with this project is that you have to build a bridge that holds a certain amount of weight for a certain amount of time. And this project is going to be due on Monday, February 8th. Monday, February 8th. And that's for this class. If you're watching in a different school year, that probably doesn't apply to you. So I'll just show you a couple examples here. So this is the sort of thing that classes in the past have come up with. They used pieces of wood, made a little bridge that went through all of the different things in this, and came up with these as examples. Now I want to mention just a couple things. It has to be a bridge, so you can't have anything connecting the two legs on the bottom. Otherwise, cars couldn't drive under it. It has to be built by you. Has to be made only of wood and glue. You cannot use nails. Vertical clearance is 5 centimeters. So vertical clearance would be this distance here, from here to the ground. Horizontal clearance, 20 centimeters. So from leg to leg here, this needs to be 20 centimeters. Legs no wider than 5 centimeters across. These are bigger than 5 centimeters, as you can probably guess. Flat surface on the top. You can't have suspensions on the top, as cool as that would look. There has to be a hole in the middle, and weigh less than 200 grams. And I do have something you can weigh it on in class here. So what most students do is they bring in the wood that they're going to use and just measure the wood itself before they put it together in order to see how much that comes to. Now the type of wood that's best for doing this is called balsa wood. And you can find this wood at just about any hobby shop. You can get it on Amazon. American Science and Surplus is a popular place that people go for this. Otherwise, if you just Google random hobby shops in the area, they probably have some. So it usually comes in a little packet of a bunch of pieces, and it's not too expensive. But yeah, you're going to want to use balsa wood. I do have glue in class if you want to use glue to put it together. Hot glue guns are in the back, so feel free to use that if you want to do that here once you have your wood. And yeah, it's going to be due Monday, February 8th. So put that in your calendars. It is on Schoology. That's about it for that. See me with questions as you need. Any questions just from that? Okay.